Welcome to our lecture online. Now we're going to talk some more about fluid dynamics, but in this case we're going to take into account the frictional forces between the molecules within the fluid and the interaction between the molecules and the container walls, or in this case the walls of the pipe or whatever the fluid is flowing through. So there the frictional forces amount to what we call viscosity. There's viscosity within the fluid, and the greater the viscosity, the more difficult it is to get fluid to flow through a pipe or through any sort of channel. Now notice in this case you can see that what we're indicating here is as fluid is flowing through a pipe like this, and assuming the pipe is kind of circular in cross-sectional area, then you can see that the velocity of the fluid is fastest in the center of the pipe and is less fast as you go further out, and eventually goes down to about zero when you get to the walls of the pipe. So what you can imagine is, let's say that at some point in time the fluid molecules are all lined up right here. As time passes, the ones in the middle travel faster, the ones away from the middle travel slower. You can see that these molecules end up over here, while these molecules will end up over there, and those molecules will not travel very far in the same amount of time. And that's how fluid flows through a pipe because of viscosity. Now that's very different from what we talked about before when we talked about Bernoulli's equation. The only time that pressure would change with Bernoulli's equation was if the velocity changed, because the pipe may get narrower, the pipe may get wider, and that is still the case. And in the case that the pipe goes up or down, you would expect a change in the pressure. But here what we're indicating is, even if the pipe does not change in size, so therefore the velocity remains constant throughout the pipe, and secondly, let's say the pipe doesn't go up or down, so there's no change in height, we would find that the pressure will change as you travel through the pipe. So we would expect higher pressure here and lower pressure there. So maybe I'll write that down. So high pressure on the left side and lower pressure on the right side. So there's a change in pressure over a certain section of the pipe as fluid flows through the pipe. And so that's where this delta P comes from, the change in the pressure from one point in the pipe to the other point in the pipe due to viscosity. What was discovered was that that change in the pressure from one point in the pipe to another point in the pipe, is the viscosity here, is equal to the coefficient of viscosity times the length of the pipe divided by the radius of the pipe to the fourth power. R is the radius, L is the length of travel. Now this is only valid if L is not too small, because if the pipe is very short, there are some edge effects as the fluid goes into the pipe. Whoa, I'm dropping my pen here from all that excitement about this. And as the fluid leaves the pipe, if the pipe is very short, you have these edge effects, so we cannot take those into account. We want to make sure that the pipe is long enough so we're not deceived by those edge effects. But anyway, the change in the pressure will be equal, or not equal, but proportional to that ratio right there. We also know that the velocity in a pipe like this changes, and therefore is proportional to the radius squared of the pipe minus where the point in the pipe you're considering. So let's say if r is small r is equal to big R, but in other words, how fast are the water molecules, or in this case any fluid molecules, doesn't have to be water, any fluid molecules moving along the edge of the pipe? Well, if r is the same size as r, it's basically zero. And then you can see that if r is zero, if little r here becomes zero, that would be the maximum velocity. You have the maximum velocity of fluid in the pipe right at the center. Now you may want to ask yourself the question, how does the change in the pressure change? Now that's kind of strange when you think about it, but notice that from here to there would be a certain pressure drop. Well, what would be that pressure drop if the pipe was narrower? Well, notice that it's proportional 1 over r to the fourth. And so let's say that r now changes to 0.9 r, and you're trying to push the same amount of fluid through there. What would happen? So what's going to happen is that the change in the pressure, delta P, is going to now be equal to 1 over 0.9 r to the fourth power. I shouldn't say equal, I should say proportional, because we don't have a constant of proportionality there. We're still talking about proportionality. And that would be r right there. So let's do that. Let's calculate that. What is 1 divided by 0.9? So 1 divided by 0.9. And let's square that, and square that. Notice that it's now 1.524. So this would be equal to 1.524 times what it was originally. the delta P initially if R was equal to 1R. What that means is, there's a kind of a practical application here. What that means is, let's say you have an artery and the heart is pumping blood through the artery, and of course you have to have a certain amount of blood pressure caused by the heart pumping, so that you know that the pressure on one side of the artery is greater than the pressure on the other side of the artery. So there's a certain amount of pressure building up trying to push blood through the arteries. Now what happens when the artery narrows? Let's say the artery narrows by 10%. It goes from R to 0.9 R. What does that do to the pressure buildup trying to get the blood through the arteries? Notice a reduction of 10% in the radius of the artery causes a 52% increase in the pressure required to push the blood through. So that's how we can look at fluid dynamics when we take viscosity into account as the fluid flows through like a pipe or an artery or any kind of container. And so you can see that there are definitely some differences that come out that we have not considered yet when we're taking a look at Bernoulli's equation before. So now we're going to show you a bunch of videos to show you how the viscosity has an effect in fluid flow. Interested in it? Stay tuned, and we have a bunch of videos lined up for you.